Yes.
Yeah. Okay, so today in our seminar we have a preface of the PhD thesis written by the PhD student Zhuoke Yang during the last 3.5 years.
Yeah, 3.5.
It's not yet 4. Okay, we start. Everybody is welcome to ask questions and comment on the thesis presentation.
Okay, so the talk title is New Approach to the Algebra Resistance. This is results of publications. Next, we're going to talk about the chord diagrams and the weight systems. So, chord diagram is very simple combinatoric object. If you have a circle and you get several chords, and each chord you get 2 endpoints. I call it vertex, and there's orientation on the circle. So I'm going to draw a lot of different chord diagrams in the following. So I always assume that the orientation, or you say direction on the circle, is anti-clockwise without special mention. This chord diagram, and there is a vertex space A is spanned by the chord diagram over a complex number. A is graded. Each component an is spanned by the chord diagram of the same order n, which is with the chord diagram with n chord. And next is the Fortune element in the chord diagram space. The Fortune element is the sum of these following 4 diagrams. So I picked the 2 specific chords in the diagram, and they're fixed one, and switch the endpoint of another chord. So there's 4 possible places to be the neighbor of neighboring to endpoint. And there's this kind of element I call it Fortune element. And the function f is finished on all Fortune elements is called the weight system on the chord diagram. And this chord diagram space have the bialgebra structure. And definition.
So, there's a return. Yeah, and all the 4 diagrams contain additional chords, the same set of additional chords.
Yes, yes.
And the ends of these additional chords belong to the dashed part of the circle.
Yes, yes. So I only like switch the endpoint of these 2 specific chord, and the other chord is remain the same. I didn't draw it in the picture. Okay, the product in the chord diagram space is defined by get 2 chord diagram D1, D2, and they just cut it someplace, and take another cut in D2, and they just glue these 2 diagrams together. You can see that this definition is defined. It depends on where you cut in the first diagram and where you cut at the second diagram. But actually, if you model the Fortune relationship, this definition is well defined. And there's a co-product in the chord diagram algebra mod Fortune relationship is the map from the space to the tensor space. And definition is to summation all the DJ tensor DJ bar. And the J is a subset. DJ and DJ bar is induced subdiagram of D, which means that take a subset of the chord, and the complementary subset of the chord is J is a subset, and J bar is a complementary subset of the chord. DJ and the DJ bar is induced subdiagram, and use summation for all the possible choice of the subset J. Okay, and this product and co-product make the space of the chord diagram mod Fortune relationship is a Hopf algebra. It is connected, and they're commutative and co-commutative, and they're based on their Morse theorem say that this kind of algebra always could express as a polynomial of the primitive element. So we can look only at the primitive element to figure out the structure of this Hopf algebra. And another important definition is a Lie algebra weight system. So the weight system is a function vanished on the Fortune element, and there is a big part of the weight system defined by Lie algebra. And now I'm going to show you this definition. So G is a Lie algebra, and with AD invariant non-generated by linear form. The first step is choose a base. E1, EM, M is the dimension of the G, and there's a dual base EI star. E1 star, E2 star, EM star, and when I say the dual base, which means that the bilinear form of the EI EJ star is equal to the Ij. The next step is just look at the arbitrary chord diagram D with n chord, and you just cut it at some point on the circle, and you just log anti-clockwise. For example, this is a chord diagram with 3 chords. So following just walking on the start with cut point, and looking at this chord diagram, you get the end point of the red chord, end point of the green chord, end point of the blue chord. Next, you get another second end point of the red chord, and the second end point of the blue chord, and the second end point of the green chord. So we get the linear order of the end point. And next steps, we just put this base for it is assigned the base for each endpoint. So there is a base EIA. So for I name this red chord A, and the green chord is B, and the blue chord is C. The IA, IB, IC is indexed from 1 to M. The M is the dimension of this Lie algebra. And from this cut point, you can see that mark the first endpoint is, for example, the red is EIA, and the second endpoint is E star IA. And for the green, the first endpoint is EIB, and the second endpoint is EIB star. And the blue, you get first endpoint is EIC, and the second endpoint is EIC star. And next, you just product all the EIA star, and this is our definition of the Lie algebra weight system. And we take the summation for all the index IA, IB, IC from 1 to M. And the order of the product is just following the anti-clockwise from the cut point. So you see that our definition of the Lie algebra weight system is based on now this definition is based on where you cut and how do you choose the base. And actually there is a theorem from De Bernard and Combinatorics. I think this result is in 1995 or maybe 1998. Says that this definition, the weight system, according to the Lie algebra G, do not depend on choice of the base point, and do not depend on the choice of the base. So which means that it only depends on the chord diagram. And the result is in the universal enveloping algebra of G. Actually, it belongs to the AD invariant space, which is the center of the universal enveloping algebra, which is a polynomial algebra. And the most important is this weight system is vanished on the Fortune element, which is called satisfy the Fortune relation, which means it is really a weight system. So this definition is very simple. You just for arbitrary Lie algebra, and pick a chord, pick a base, pick a cut point, and you can get a construction. it's very easy to construct, but it's very hard to compute because this element is in the universal enveloping algebra of the algebra, and this is a non-commutative algebra. Each time you commute the two elements, you get a lot of mess. So this is why it's really hard to compute. And before my result, there is only two cases known. One is SL2, the simplest algebra. Another is the superalgebra case, GL11. There's a recursion relationship. And for the general case, they want to know how to calculate it. And I'm going to talk about the GL the Lie algebra GLN. The Lie algebra GLN is first is a vector space of all the n times n matrix, and the AD invariant bilinear form we take as of the two matrix xy. We take as the trace of xy. I mean, here xy is just the product of the matrix, and then we use the base Eij. With that the matrix have only one at ith rows and the jth columns. So this Eij is the base, and we get this bilinear form, and the base, the real base, according to this bilinear form, is Eij star is Ej, because Eij EKL, the product, the matrix product is delta Ij delta Jk, taking the trace. And the computation relationship is, should I follow? EKL EJI is EKL EJI minus EJI. EKL is the delta Ij EKI minus delta Ik EJI. So this is simple very standard matrix. And the Casimir element. So next, because our Lie algebra wave system taking value in the center of the universal enveloping algebra. So the first is the structure of the center of the universal enveloping algebra of GLN, which is spanned by the element we call Casimir element. So first is the simplest chord diagram, which is a circle with exactly one chord, a single chord. So
this is not the simplest one.
The simplest one is the trivial one. It's the chord diagram without chord. Okay, so this is the chord diagram have only one chord, and based on our definition, for the you can cut it anywhere. We get two endpoints. The first endpoint is EI, the base EI, and the second endpoint is EI star. And for the GLN case, the first endpoint is Eij, and the second point is Eij star, and we know that the dual base of the Eij is Eji. So definition, based on definition, the wave system, a GLN wave system on this chord diagram is the summation of Eij, Eji, and we call this element the C2, the quadratic Casimir element, in the center of the universal enveloping algebra. And the C1 is summation of the EII, and generally the case Casimir element CK is a summation of the EI1, I2, EI2, I3, blah blah blah, and the EIK, I1. And I just say that now here the product is the tensor product, or the product in the universal enveloping algebra, not just the product of the matrix. So you need to, I just do not use the tensor product mark here. So it is in the universal general algebra, so which means you could not have actually product these two matrices. And the center of the universal algebra of GLN, so it is just the polynomial of the Casimir element C1 to Cn. And the higher Casimir element Cn plus 1, Cn plus 2 could be represented as a polynomial in the lower Casimir element if you fix the n as a number. And the relationship of the higher Casimir element, how to represent as a polynomial in the lower Casimir element, we take phi as the Harrison counter isomorphism, we get Permorph formula look like follow, because the phi is actually isomorphism, so you can you resolve this formula, and you can get the
how phi looks like. What extends ck to what?
The phi is just
just right, but I'm afraid letter phi is not appropriate here because we use phi for the weight system.
No, I changed the
you changed
weight system is W, not the
Okay. Fine.
So the universal broken algebra of GIN, and you can always write as n plus h n minus, which is all the
GLM, the algebra itself, not the universal enveloping.
Not the universal enveloping algebra, but GLF.
Yes, the GIN, but also the universal GIN algebra, because we have the we can change the order of the bases too. So GIN is H plus, and the universal GL and the U and minus UH.
These are diagonal matrices and the upper triangle.
Yes, this is the
No, again, it's not like that.
What exactly? Tensor product should be.
Yeah, tensor product. Yes. And this first is the project from this to this center, and this projection is given the isomorphism UGN of the here is a polynomial of the EII. This projection is given this. Okay.
No, not exactly, but well, it's not isomorphism, it's mapped injectively to the.
But we take the center to the isomorphism. But this is a projection. But
the image is not the whole algebra of symmetric function. It's not whole algebra.
You see it looks like this. Like this?
Yeah.
Okay.
Shifted symmetric function.
Yes, because this is the print of Kazarian. Yes. So this is the structure of the center of the universal GL, universal enveloping algebra of GLN. And next, I'm going to show you based on the definition of the Lie algebra weight system and how to calculate this for the F-tree chord diagram. So here is another a little bit complicated chord diagram with two chords, and this two chord is cosine. And I'm going to show you how to calculate this weight system, GRN. So based on definition, there's 4 endpoints. You get the weight system EIJ, EKL, EJI, ELK. And this is the element in the universal enveloping algebra. So next, you just switch the middle two elements, the EKL and EJI, and replace it as the Lie bucket of the EKL, EJI. So you get 3 terms. The first is switch the second EKL, EJI, and the next 2 terms is get it from the Lie bucket. And the first term, that is EIJ, EJI, EKL, ELK, which is just the C2 times C2s. And the next 2 terms, you just rewrite the index. Now you get the 3 elements and the 3 index. And the first, you get EIJ, EKI, EJK. And next, you get the EIJ, EJL, ELI. And you still, again, you see the first term is Eij, so you just put the next two elements together. It is the Lie bucket of the Eki, Ejk, and rewrite this Lie bucket. You can get two terms, and finally you get the C2 square plus C1 minus NC2. Okay.
Something go wrong.
Сереж, ты закрыл демонстрацию экрана.
Я закрыл демонстрацию экрана. Sorry. I should return it back.
Дополнительно.
What should I do?
What?
Теперь видно будет?
Yes, but maybe full screen mode you could. Yes, that's better.
В общем, можно ее двигать потом будет. Ладно.
So you can see that it is very complicated if you just dealing with element in the universal enveloping algebra, because each time you switch it, you get a lot of terms that you don't know, and it's very hard to calculate it in the universal enveloping algebra. And next.
But even for this example, it's seen from the answer that dependence on the n, the capital N, is not so hard. So the element belongs to the center of GLM, but the dependence on n is not so complicated. It's just if you write in terms of Casimir elements as a polynomial Casimir element, that it's the dependence on n is polynomial, or in this case even linear.
Yes, it is linear under n. Yes, it is. And also I want to mention that if you look at this term, that's the IJL, the EIJ, EJL, ELI, it's actually the C3. But finally, there's no C3 because you need to deal with this term and you get to the C3 cancel. So it's not only one way you can to switch thing and you get something Casimir element and finally you just cancel it. So it's not a good algorithm to calculate it because you get something you want and finally it's dispaired. And next is we generalize the definition of the wave system to the permutation. So we have a permutation sigma. It's permutated on m element, and the permutated set, the m element, I get ordered, so it's indexed from 1 to m. And we define our wave system WGN of sigma as a summation of the EI1, I sigma 1, EI2, I sigma 2, and EIN, I sigma n. It is also an element in the universal enveloping algebra. And I claim that the first, this WGLN of the sigma, is lie in the center of the universal enveloping algebra. And the next, this element is invariant under the conjugate of the stand cyclic permutation, which means that the not 1, 2, 3 n, it's 2, 3, 4 n 1. So we just switch the first element to the end. We get EI2, I sigma 2, EI3, I sigma 3, and EI1, I sigma 1. Which means that the permutation I'm looking at is not permutated under m element, it's the permutated under cyclic ordered element. So this m element is indexed from 1 to n, but it is cyclic. So you just change the index with one digit, it's still get the same permutations. It looks like the permutation under M vertex on the circle. Okay, next, the digraph of the permutation, which the way we draw a permutation as a digraph. So the drawing is simple. That we get the diagram of the permutation sigma belong to the Sm, have the M vertex and the M directed edge. So the M permutated element is placed on the real lines, and the directed edge from I to j if and only if sigma I equal to sigma I equal to j. So you see that each element which has the vertex is indexed from 1 to n, and there is one outgoing and one ingoing for each vertex. And this is an example. So this is a permutation only have the circle length 2. So 1n plus 1, 2n plus 2, and 2n. You get the digraph with the 2n vertex, 1, 2, 2n, and each vertex you get one income edge and one outcoming edge. Look like this.
If we have fixed points, the computation points.
For the definition of this digraph, yeah, we allow that there's a fixed point.
Just draw a picture. What happens with the fixed? How the graph will look like.
Oh, okay. So the fixed vertex is the fixed is just the you can say it's mapped to itself. It's fixed. So sigma equal to I. So it is look like a loop. Okay, this is digraph of the permutation. And since I mentioned before that our definition of the wave system is invariant conjugate standard permutation. So this, you see that this is a digraph on the real line, but actually you can connect the real line as a circle. So you can see that this M permutated element is placed on the circle. And the cosimian element Cm in the center is the summation of the ei1, i2, i2, i3, ein minus 1 im, ein i1. So it exactly corresponds to the wave system of the stand cyclic permutation 1 to 2, 2 to 3, 3 to 4, and the m minus 1 to m to 1. So this is the stand cyclic permutation in Sm. The wave system, our definition of the wave system is correspond to the cosimian element Cm in the center. And the diagram is look like this. The edge from 1 to 2, 2 to 3, and m minus 2 to m minus 1, m minus 1 to m, and finally from the vertex m to vertex 1. So this is the diagram of the cosimian element Cm. And the chord diagram. So what's the relationship of our definition for the permutation and our definition for the chord diagrams? So you see the chord diagram is n chord on circle, which there's a 2n endpoint. You consider that the chord diagram is a permutation without a special permutation, which is an involution without a fixed point on the set of the 2n elements, and each chord give an involution of the endpoint. This 2n element is just the endpoint of the chord, and each chord gives the involution of this 2n point. And if you transposition of the endpoint. Yes, transposition of the endpoint. And the value of the algebra wave system WGN for the chord diagram, it is the same as our definition for the corresponding permutation. And here is an example that Kn is a chord diagram. Sorry, I draw it as a linear diagram, which means a cut point of the chord diagram. The chord diagram is actually n chord that each chord are crossed. So there is a 2n endpoint, 1 to 2n, and if you cut it somewhere, the linear diagram looks like this. The chord 1 to n plus 1, 2 to n plus 2, and n to the 2n. And we write that the wave system WGN of the Kn is the summation of the ei1, in plus 1, and ein, i2n, ein plus 1, i1, n plus 2i2 and find the last term, the last element as ei2 and ein. It is exactly the way system WGIN of the permutation 1n plus 1, 2n plus 2, and 2n. So this is how we so check the to put the chord diagram as a special case as a permutation. And next, the way system for permutation. It's I have an algorithm, or say a relationship, the recurrence relationship for the value of the GN way system for permutation. The first, the start is the empty graph, which is the graph without vertex is value 1, and the WGIN is multiplicative respect to the just connected to permutation. If you just draw the permutation as a diagram, just connected the real line. And the standard cyclic permutation is a Casimir element. And the recurrence rule is localized photo. So the graph is arbitrary permutation sigma, and we only look at the two neighboring elements k and k plus 1 of the permutated permutated set. So each vertex with one incoming edge and one outcoming edge. And if you just switch the place of these two elements and take the difference, which is the first graph minus the second graph, the difference of this first and second graph is only the order of these two vertex k and the k plus 1. And we do not, there's other vertex on the line, but they are not changed. And also the endpoint of this directed edge, another do not draw endpoint is also remains the same, and only replace to switch the two places, two vertex, and you get two new diagram, which is have the vertex k prime. Next, there's a special case if the sigma k plus 1 equal to k, which you connected this two edge, and you get the difference is C1 times the permutation, remove the vertex k and k plus 1, and minus n times the k prime. And I would mention that it's for the third diagram that if you connected sigma k plus 1 with k, you just get a loop. And this loop is represented to C1. And for the fourth diagram, there is a circle, and circle means that times n. And first is based on this rule, you can get the GN way system of the Casimir element C1, C2 to C infinite, not restricted to some special number of the n, which means that we get the universal GN way system of this permutation we are defined, and it's a polynomial in the infinite variable n, variable n, C1, C2, and go on. And this polynomial, I call it a universal GL way system. And next is an example to compute this universal GL way system on the cyclic permutation 1, 3, 2. So if I want to calculate the way system of the cyclic permutation 1, 3, 2, I just switch the endpoint 2 and 3. And the permutation 1, 3, 2, if you switch the endpoint 2 and 3, you get the permutation 1, 2, 3. And permutation 1, 2, 3 correspond to the Casimir element C3. And you take it different, and you get the two simple chord diagram. And you can see it's easy to compute it, the way system. The result is C3 plus C1 squared minus NC2. And I want to say that this recurrency rule do actually give us a algorithm to calculate the way system, because if you look at this relationship of for permutation, the left side of the equation is the different. You can switch the two endpoint, and in the right you get the permutation have a smaller number of the endpoint, and because the goal of our calculation is to describe the permutation as a product of Casimir element. And if we can change the endpoint, we can always decrease the crossing of the directed edge, and we get the
number of crossings.
Is yes, the number of crossing, yes, and by only switch the endpoint, we can make our permutation as just a separated circle of the permutation. And the difference is some permutation have the lower number of the vertex, so you can finally get the result to express this as a polynomial of Casimir element. And yeah, you can see that you can calculate the result. And this K2, K3, K4, K5 is chord diagrams with Kn. Kn is chord diagram with n chord, and each chord is cross each other.
Already in this answer, one can see some important properties of the results. For example, for K5, you have a polynomial in C1, C2, and so on, but the highest index of C which arises is C4. There are no C5 or larger. And C4 also you find in the GL weight system of K4, but presumably this will always be the case for arbitrary, and what you obtain will contain only Casimirs of order at most the number of chords.
But the degree of each monomial in the definition is equal to 10.
Mm-hmm. In spite of the fact that the degree of each monomial is equal to 10. Yeah.
Mm-hmm. And also that you can think that the Hopf algebra this Hopf algebra of chord diagram is expressed as a polynomial of the primitive element, and you can check that the projection of this wave system, universal GL wave system, and project to the primitive element, and at that case that you will see that the degree of after projection, the wave system, the polynomial of Casimir element, the degree is only, for example, K5 is only 5. Here it's 10, and after project to the primitive space, it's only 5. And you can check, see the simple result. And then here is you get 2 many tens. Okay, next is about the Lie superalgebra wave system. And I'm not going to give you the definition of the general Lie superalgebra and the definition of how you define the wave system according to the Lie superalgebra on chord diagrams. So I'm going to focus on the Lie superalgebra GLMN. It is a special series of the Lie superalgebra, and it's very close to GLN, and I'm going to show you the results and the wave system according to the Lie superalgebra GLMN. So the Lie superalgebra GLMN is the vertex space of the all block matrix m plus n times m plus n, and I write as A, B, C, D. A is m time n matrix, D is n time n matrix, B is m time n, and C is n time n. There's the homogeneous element. There's a Z2 degree. If I say the degree of X is 0, X is a homogeneous element, and the degree is 0 if and only if the matrix B and C is 0, and X equals 1 if only and if the matrix A and D is 0. And the super bucket x, y equal to x times y minus the -1 power degree of x and y times x. So this is the super bucket for the Lie superalgebra. And it is only for the homogeneous element, and for the arbitrary element you can write it as a linear combination of the homogeneous element. And next there's the bilinear form. I call it the super trace for the Lie superalgebra. S trace x as the trace A minus the trace D, and this is the bilinear form. And this bilinear form is not symmetric. It is AD invariant, but it is not symmetric. It is supersymmetric, which means the bilinear form xy is -1 power degree of x times degree of y yx. And the GRMN is the matrix unit EIJ, and IJ from 1 to m plus n is the standard base for the Lie superalgebra GRMN. And the J2 gradient is the EIJ. I write the grade as I bar plus J bar, and I bar is just element of the J2 if it's 0 bar or 0 or 1 in J2, depending on the I is in the first block. It's from 1 to m, or it's from m plus 1 to m plus n. And the commutation relation EIJ EKL is the delta JK EIL minus 1 power I bar plus J times K plus L times K plus L delta IL EKJ. So this is the super bucket, or is a commutation relation. It is looks very like the GLN case, but with the second term have a sign -1 power I plus J times K plus L.
Sorry, you mean 0 with a bar is a 0, or?
Sorry, what? Yeah,
0 with a bar.
0 in the bar is the element 0 in J2. It is just the J2 is a plus.
Okay.
The operation is plus, so 0 is the identical element in J2.
Sorry.
It's the even element in J2, and 1 is
0 with the bar doesn't have any meaning.
Yeah, there's no meaning. 0 have bar. So 0 is the.
That's why I asked. Yeah.
Черточки ставим только над числами от единицы до m plus l. The bar only indices from 1 to m plus 1 are barred. M plus 1, m plus n, yeah.
Yes.
The dimensions of the matrix. 1 bar is 0, m plus 1 bar, m plus n bar is 1.
Yeah, just bar is
Yeah, there's I bar, J bar, and the bar on the 0 and 1 is no, it's meaningless. Yes. And next is the structure of the center of this universal enveloping algebra of the Lie superalgebra GRMN. And it is also a polynomial algebra generated by Casimir element CK. And in this case, Casimir element CK is the summation of the you get a sign -1 power I2 plus I3 plus IK bar, and the product of the base the matrix unit element EI1 I2 EI2 I3. This is the same as the GRN case, except this sign. But in this sign, the -1, the power is only from the I2 to IK. There's no I1 here. And especially for example, the C2 is the summation of the -1 power J bar times EIJ EJI. You only have the J, don't have the I. So this is the structure of the center. And next, I directly define with the GRMN weight system for the permutation. So here the weight system for permutation defined as -1 power sine function f sigma times that ei1, I sigma 1, ei2, I sigma 2, and eik, I sigma k. This for permutation sigma belong to the permuted on the k element set. And here we need to figure out the right sign function for gi and n. And what I mean the right sign function, which means that first I want this wave system is in the center of the universal, in the center of the universal enveloping algebra. And next I want this this definition for permutation is also same as the wave system for the chord diagram. And the definition of the sign function, we know that because we know the structure of the Cosmic element, and the Cosmic element corresponds to the stand cyclic permutation 1 to 2, 2 to 3, k minus 1 to k, k to 1, which means that we know that the sign function for the stand cyclic permutation is I2 bar plus I3 plus I4 plus IK bar. And for the arbitrary permutation, and there's two parts. First part is the linear part, the second part is quadratic part. And so the first part is index A that satisfies the sigma is 1a is smaller than a, and maybe I can draw to show this sign function by permutation diagram. So so if we get permutation, and we just this is 1, 2, 3, the sigma. Here is 1, 2, 3. So the first set, the P1 sigma, is all the endpoint that the edge from left to right. I mean the endpoint is the target point A, that the directed edge sigma minus 1a to a is from left to right. Then this is the first set. And then the second set.
Will you show it, please, on the?
Oh, okay. So that's P1 is 1, 2, 3. It's all the endpoint that if you have a directed edge from left to right, and you just label this target endpoint. So this is 2, 3, or I say I2 bar, I3 bar. So this is the first set P1. And
just 2 and 3, not.
That's 2 and 3. Okay. That's the 2 and 3. And the second set is that the pair. So first we just draw the for each vertex the outcoming edge a little bit right, and the incoming edge is the endpoint is a little bit left, and the P2 is all the pair of the endpoint that there are causes. If there's two directed edges crossing, then you just label that endpoint, the two target vertex, target point. And in this permutation, there's no. Maybe I show you another example. It's
if you take just the inverse permutation.
Yeah, the inverse permutation. It's 1, 2, 3. This is permutation 1, 3, 2, 1, 3, 2. And you see the P1, 1, 3, 2 is 3. You got directed edge from 1 to 3, and you just label the target point 3. And P2, 1, 3, 2 is all the pair that if you are crossing. So you see, you got the cross here, it has 2 and 3, and then you get a cross here. there's 1 and 2. And you can put here, so that's order pair 1, 3. Look like this.
But you need to add additional brackets. P1 of the permutation 1 to 3.
Yes. Yes. Yes, yes. That's for the permutation. And this is our definition, F sigma, for the permutation sigma in SK. And there.
And what's we always taking cycles, yeah?
So
we always take cycles, we don't take.
Well, not necessarily cycles.
No.
Arbitrary permutation.
Arbitrary permutation. So if you take fixed point, P1 and P2, what's happening?
If you get a fixed point, then this so you get a fixed point, and I always write that the outcoming is a little bit right and the incoming is a little bit left. So you will get to the loop like this. This is the one vertex. So it's not belong to P1 because this is direct add from right to left, and it's not going to cause anything because there's no vertex between these two endpoints. So this vertex I is not going to belong to P1 and also P2. So
and just if you have a fixed point, then you have just a factor C1.
Yes.
You can factor out its point anytime.
And this sign function, and I guess theorem say that this is the GRMN, the superalgebra wave system for chord diagram, is actually a special case of the GRMN wave system for permutation. If we consider that the chord diagram as involution without fixed point on the set of this Zhuoke endpoint, and also I proved that the GRMN wave system had the similar recurrency rule as the GRN case, which by the result that you put the n minus n is C0, which is n, and the case element is keep the same, CK. Yeah, and this is.
That's all?
Yeah, that's all. And I left a lot of time.
I have a question then.
Uh-huh.
There was a slide where you wrote something about the products of permutations.
Permutation, yeah.
And their weight systems. How do they interact?
Sorry?
This was before.
The permutation, the product of the permutation.
Yeah.
No. So you get
there are two different products.
Yeah, I think it's just the product of the so for the sigma we just write the digraph, and this is sigma 1, and you get another sigma. For example, look at this. This is the sigma 2, you draw this the digraph, and the product you just connect it. So it's the sigma 1 from sigma 2 is the sigma under, this is the sigma from the Sn, sigma 2 is from the Sn, and the sigma 1 and the sigma 2 is Sm plus, and it's a symmetric, it's a permutation on the m plus n element, and the permutation is remain the same.
You call this concatenation.
Concatenation, yeah.
Yes.
And
the weight system is multiplicative with respect to concatenation.
so that was just that.
Yes.
And nothing can be said about the products of permutations.
No.
Not like that.
Essentially nothing. This is a very complicated question. So to compute the weight system on a product of permutation, provided you know its values on the factors. More questions, please, and comments.
The fact that the weight system on GLMN, the weight system in GLMN is basically the weight system in GLN. There is nothing really. It's very strongly related to GLN. Is it something that was predictable or not really?
No, it was surprising.
It was
So it's
surprising.
not to me question.
So I mean, if you see that the GN weight system and the GM weight system, if you for the specific M and N, and so you need to project the higher cosmic element to the, because it's do I have it? Here the structure of the center of the universal enveloping algebra of the GRMN is actually so there's a mistake. So the cosmic element for the specific N and M, there's only M plus N element, which is C1, C1, C2 to Cm plus N. And you see here that the C0, which is the N for the GRN, is M plus N. And also the projection of the higher cosmic element to the lower cosmic element is a little bit different. For the GRN, we get the promorph and the formula, and this also have a similar formula, but if you do the projection, it is different. But we have the universal case, which means that for the GRN, we have n going to the infinite, and we put the n as a C0. It is polynomial of the infinite variable C0, C1, and go on and go on. So at that case, you don't need to do the projection. And here, we assume that you do not do the projection of the higher cosmic element to the lower elements, and the cosmic. So this is also a polynomial on the infinite elements, also C0 to C0, C1, and go on. Then you get to the universal case that in this sense they are same.
Actually, you can use the first M plus N Casimir generator, then the remaining could be expressed in terms of the first M plus N, but not as a polynomial, but as rational functions.
Yes.
But the original question was after the case of GLM was studied, to extend this study to GLM case and to extend the universal GLM invariant to the case of GLM MM. And there was a hope that there will be some more general invariant. But after some experience, it was observed that actually the case of GLMN is contained in the universal GLM, and this was surprising. So the hope was opposite. The hope was that there should exist some more general invariant.
This was totally unexpected, and this inclusion is in fact rather strange, because you substitute the difference of M and N, which could be well be 0 or negative, for n capital, for C0, for n capital, which is the dimension of the matrices in the GLM case. And somehow it happens that this dimension could be negative. And before those results, only SL2 or GN11 were studied, and there was no visible connection between the two.
Can I ask a question? Do you hear me?
Yeah, you're welcome.
Thank you for the very interesting talk. But actually, one can also define a weight system not only for chord diagrams, but for circular chord diagrams, but for chord diagrams having several segments as its support. Yeah, if you have read the book of Chmutov, Duzhin, and Mostovoi, they call this algebra AN. So have you tried to look there and if this result generalized to this algebra of chord diagrams as well?
If you have not a single circle, but several circles,
not several circles. For several circles, it's ill-defined, but just several lines, several segments.
Several segments.
Strings.
Strings.
Yeah, strings.
Actually, I don't know. I don't think that. I don't know. I don't know the answer of this question.
But you have tried to study the case of two strings.
Yes, I tried, but it failed. It seemed like I tried to the definition. Finally, it's like not in the center, and also not in some like a commutative subalgebra.
Yeah, but so, it's known to belong to the J invariant part of the tensor square.
Sorry, can you say it again?
To the J invariant part. For two strings, the answer belongs to the G invariant part of the tensor square. But it is not a commutative.
Yes. But it's not commutative. It's not a polynomial. So, I mean, the definition it seems to work, but it doesn't have no good property. I know.
Well, I have studied the GLN case for several strings, and actually there is a nice kind of basis of elements that provides you a polynomial such that the algebra spanned by them precisely contains all the images of elements. So it's Karishchandra, something like it. Oh, I don't remember. But yes, the fact that this space actually has a polynomial basis for arbitrary number of strings.
Okay.
Have a look. More questions, please.
Maxim, could you give a reference?
Well, I think the book of Chmutov, Duzhin, and Landau has it when they discuss weight system for this, not for algebra AN itself, but for algebra BN, which is isomorphic to it.
Okay, thank you.
Chmutov, Duzhin, and Mostovoi you meant.
Oh, sorry. Yes, of course, Chmutov, Duzhin, Mostovoi.
More questions? Serежа Хорошкин, do you have questions? Nope. No. Okay, then thank you. Thanks, Zhuoke. Now we are done. You may proceed further.